So 3 types of membrane transport you're going to want to be familiar with. So your membrane. Most all the membranes in your cells a lipid bilayer, right? And so here, the part that faces either out of the cell or into the cell, depending on which side you're on, all face either the cytosol or the extracellular material, which is usually water-based, right? And great, because they're charged and they like water. And then everything in here is the fatty acid tails and is nonpolar, hydrophobic. So we got a hydrophilic environment out here and hydrophobic inside. So because it's hydrophobic inside, some molecules have a really tough time crossing through. Which molecules have a really tough time crossing through? Polar and charged molecules. Ions don't pass through here, and most polar molecules don't pass through as well. Whereas nonpolar things like carbon dioxide and oxygen, they just diffuse right through. So, and that's your first way to get through the membrane. Simple diffusion. Simple diffusion. Just works with the concentration gradient. So if the inside of the cell doesn't have a lot of O2, but there's a lot of O2 that maybe got dropped off at the capillaries outside the cell, then it's just going to diffuse right across. So not a big deal. So simple diffusion. Your second type. Facilitated diffusion. Facilitated diffusion. What does facilitated mean? Helps. We're going to help diffusion happen. So notice oxygen or carbon dioxide can diffuse right through. It still has to go, down the concentration gradient, but it can just diffuse right through. Now what if I had, a bunch of ions on one side and not a bunch on the other side? Well, they want to go through, but can ions go across? No, they're charged. They can't pass through the membrane. And so what we hope exists is in the middle of that membrane somewhere, there's a protein. So a carrier protein or a transport protein of some sort, or a channel protein we might call it. So, and actually I shouldn't call it a transport protein, but a channel protein. So in this protein, so let's say it's some sort of positive ion that wants to get through. So this positive ion first binds to the channel, and the channel says, oh, you can pass. You can pass. Cool. What do you suppose if it's binding in here? What do you suppose amino acids might face inside that channel? More specific. Got to bind these positive ions. Boy, I wonder who would be good at that. Who are the negative amino acids? Yeah, aspartic acid, glutamic acid. They'd be great. Notice if I wanted negative ions in a channel protein, they got to bind first. Might be good to have lysine or arginine in there instead. Cool. So, but again, they're not doing any active transport. We're not going against the grain. These ions are only going to diffuse in the direction they go. They're just getting some help along the way. Cool. So this does not cost any energy in either of these diffusion cases. They're going with the concentration gradient. And then there's active transport. So your active transport requires energy. You're going against the concentration gradient, it's going to cost. And usually how is that cost going to be paid? ATP hydrolysis. ATP hydrolysis. So no AT requirements in either simple or facilitated diffusion. Primary. So in primary active transport, there is a protein, and that protein's job is to transport something across the membrane against the gradient. And that protein usually has a binding site for ATP under which it can carry out ATP hydrolysis. So that protein burns the ATP, if you will, and transports that particular whatever substrate across the gradient. Notice it's against the gradient, though. Cool, and that's why it required ATP. So then there's secondary active transport. Secondary active transport. So let's say we have a cell. What is there usually a buildup of outside the cell? What is there usually a buildup of inside the cell? Talking about it in the same light anyways. Potassium. This is not some miraculous accident, right? Why is there this buildup inside and outside the cell? Yeah, your sodium-potassium pump. There's an enzyme here, a pump in the membrane that pumps sodium ions out and pumps potassium ions in. That's its job. How does it do that? Because notice, do sodium ions want to go out there? So good. Good. It's coupled to ATP hydrolysis. It's active transport. So sodium doesn't want to go where it's already more prevalent. We have to force it to. Same thing with the potassium. So, but we keep this constant, which is a good thing. Because there's another protein over here that says, hey, sodium, you want to come back in? So, well, you better bring a friend. Who's the friend? Glucose. Cool, bring your friend. And so sodium's like, sweet. And so does sodium want to go back in the cell? Yeah, that's with the concentration gradient. Does glucose. So usually the other way around. And so in this case, we created this concentration gradient with sodium using ATP. And that allows us to co-transport glucose back into the cell against the gradient for glucose, depending on the scenario anyways.